Welcome to another episode of the Unstructured Message Podcast. Today, we're thrilled to have Brian Frank, a visionary in data analytics and IoT, joining us. With decades of experience in solving complex data challenges, Brian's work extends beyond just smart buildings. We'll explore how his innovations in data modeling and semantic frameworks apply to a wide range of industries, from energy and manufacturing to asset monitoring and beyond. We'll also dive into the potential of technologies like MQTT and large language models to revolutionize real-time data analysis across sectors. Get ready for insights into the future of IoT and data-driven applications. Brian, really nice to have you here. Very excited. I think it's worth sharing how I got to know you. I mean, I guess I didn't really get to know you because it was a while after I was using your software that we actually met. But, you know, as you know, I got my start in the smart buildings world. And, you know, at the time in the late 2007, 8, 9 phase, the Niagara Framework protocol was like really the leading smart building programming framework. And, you know, so much of everything there was just really, I think, way ahead of its time. So I'm excited to have you on, talk a little bit about the old days of smart building and maybe expose some people to how far ahead of its time the stuff you built was. And then I think as we get a little bit further into it, we can get to, some of the stuff that I think joins MQTT and a lot of the stuff you've been working on together, which is really around the data modeling and the semantics and all of that. So again, thank you for being here. And just say hi to the audience, and be great to hear, a little bit of your background and what you do now and how you get there. So
okay.
Go right in.
Thanks for having me, Brian. I've been in the commercial building, smart building space for, I guess, going about 25 years now. So, it's been a while. But Tritium was basically founded in 1996. I was still just a couple years out of college then. But it was me and a couple other engineers were the first programmers who started putting that product together. And that was kind of a moment of convergence in the building automation space, because at that time, open protocols were just sort of coming on the scene.
Yeah.
And in the building automation world, at least, there was a war between LawnWorks and BACnet were the two protocols that were butting heads, and everyone was like picking one or the other. And we said, yeah, well, let's just do both. And while we're at it, we can add some other protocols like, Modbus and OPC UA, and maybe that was invented a little bit later. But so that was sort of the genesis of Niagara. Also at that time, mid-90s, you had like sort of the internet and web browsers sort of exploding on the scene. So that was another piece of the technology that sort of, we had all these things coming together that let Niagara come in there and solve problems in a unique way.
Yeah, that's awesome. And I mean, I think like there were some other things that you did that were really interesting, like the whole idea of like a block programming, right? And to be able to have like a series of routines, either like some templates or other things that you could string together and create routines, subroutines, automations, and stuff like that. Where did that all come from?
I would say there was definitely prior art in the industry for that. I mean, when you look at control sequences, there's hardly a domain that's not more suited for data flow programming than control. Even when you look at industrial controls, they were literally, wiring together thing on a board, and then the 1131 was the industrial standard that kind of took that to the programming world. And so we didn't invent that. I mean, I think we made it a little unusual, and then we built the entire product around this idea of software components and data flow and did everything with that.
Yeah.
But certainly, a lot of products at the time were doing that because it's such a great technique for what I'd call low code programming and control flows.
And composing too. So yeah, what I'll do is I'm gonna grab some screenshots off of Google and stuff like that. Hopefully nobody sues me for it. But I'll show some pictures of what you guys were doing back then, because like I think I've joked sort of over the years that I could take like the R2 version of Niagara and run it over to Silicon Valley and probably get some pretty good investment today based on, what that platform was and how it worked and how it scaled and how things communicated and stuff like that. I mean, you built it all in Java, which was not really, I would say, a standard automation industrial controls language. What made you start there as compared to any of the other sort of standard programming languages?
That was when Tridium was founded, Java, I believe, was still in beta, or they might have just come out in 1.0. So it was unusual because, at the time, I think our plan was to develop this software in C++. But, I think the idea of garbage collection and a virtual machine was sort of really powerful. It hadn't been proved out, but I had played with that language at my previous job, which was a telecommunications company. And we said, let's do it. And, it worked out really well. But funny enough, for the longest time, the best virtual machine was Microsoft. So the first few years, everyone was using Microsoft's Java virtual machine.
That's funny. And so, tell me, I mean, the early customers, who was the first to sort of look at what you guys were building at Tridium and say, oh yeah, that is kind of the way we should tie together all of these devices and machines and things like that? I mean, what were the first use cases all specifically smart buildings, or were people kind of playing around with it in other arenas too?
Actually, I believe the very first project was an industrial site that made the dryer sheets, Bounce or something like that. So that was kind of unusual. But their earliest customers were systems integrators, or sort of forward thinking, who wanted to try the technology. But in the end, Honeywell was the first major OEM to adopt the technology, which was also unusual because at the time everyone did their own software. This was like a new idea.
Oh, yeah.
A major OEM would license someone else's software platform.
Cool. And so one of the other things I really loved about that platform, and we can talk a little bit about Sedona too, because I think that had a lot of, again, really future thinking stuff. But this idea of a tree of a network, and then a lot of sub devices, and then under those devices, a lot of literal tight, objects like data points, or, things that were connected to it on serial devices or whatever. And this ability to be able to directly address something sort of through its position in that tree. That's when I look at one of the things that makes MQTT so great is that, it's like this sort of slashed tree, whereas you guys didn't use slashes, but it's still the ability to communicate with something based on its physical location, or, its parents' objects and things like that. Where did that come from? I mean, that was, again, if I look at the train tracer stuff that was out at the same time, it was like you were coming at this from another planet. How did that come about?
So I'm fascinated by, organization of information, right? And you've got all these models, relational information, and, RDF, and was not even really done then. But I would say that inspiration is really just how Unix, basically the idea that everything in Unix is modeled as this tree of files, and taking that sort of to the extreme that basically every piece of information would fit in this tree some way, which meant we could give it, a path that we could access it, and then we could use that for the data flow programming, et cetera.
Yeah. And then I think one of the largest projects that I worked with, the Niagara Framework, was once in the AX, which is sort of like that second generation of it. Or third generation, I guess, technically, right? Because R2 was the second. But the third generation, and at that point, the scale, it was just because everything had been tuned so well. And, we were at Turner Properties in Atlanta, and, working across CNN Center and all these other facilities. And, to be able to build these trees and then use a language like BQual, which I will show up a nice little picture to people about BQual, and the idea of this thing. But what you brought there, again, I think is something that's even missing now from something like MQTT or really a lot of the other sort of IoT communication constructs that are out there now, which was your ability to treat the structure, the hierarchy of the devices as like a data model where you could say, show me all the temperatures from this wing of the tree where the parent is named something asterisk, room 17. And you could just do like all these really cool queries and just get a real-time result from it that was just like changing in front of your eyes. And when you're talking about like pulling together tens of thousands of temperature sensors, like it was just so amazing. It was so, again, forward thinking. Where did that come from? Like, how did you, was there a specific customer or like a requirement, or was there something where somebody said to you, or are you just like, I really think that like this physical network space needs to be something that, you can just write SQL-like queries against?
Yeah, I think one of the things that drove the tree structure actually was the idea that everything should be cut, copy, paste, right? So that sort of also went back.
Well, made it easy.
Sort of like the file system, right?
Yep.
People are used to working with file paths. They're used to, navigating file paths with code. And it sort of gives you that inherent containment structure for copy and paste, which was a huge part of how Niagara worked. The idea was you built out a tree, you could copy sections of the tree, and you linked ideas and pieces of the tree together, and that was it. So, and when we went to design the connectors, the drivers, right, the idea was that any outside information would have to come into this tree structure because that was the way everything worked. So it was always this mapping process of, for this protocol, what's the best way to bring this into the tree structure?
So then to be able to ask questions of it and query it, like nothing else then, or even really now, allowed you to do that. Like whose idea was BQual? Like was that you, your brothers, or
probably John Sublet and I, did that work, and I think he's the one that implemented. He was like sort of the, also one of the original engineers with me that worked on the product from the very beginning. Still definitely floating around in the space too.
Yeah, he is. I talked to him not recently, a couple of years ago, but he's still out there. That's awesome. Okay, cool. So at the heart of this, like you talked about the communications, along the lines of like, I think a lot of people who listen to this are probably familiar with Kepware. You also created a model for developers to be able to build protocol translators where they could, write against, like if they're an OEM or some other automation company, they could write against their own proprietary protocols and convert it to, I guess, what you called Fox, which was really the kind of protocol of the Niagara Framework, correct? Or you had some that you commercially provided, but you also built like this network of developers and systems integrators who like would build them directly for customers. And like you had this great documentation and stuff like that. Like, how did you, like, what part of that was planned versus what part of that just really like evolved or came about? Because I feel like that's something that like other vendors, even today, like in the IoT platform space, are still trying to figure out and crack that code. Like to have something where the guys who are also working with the screwdrivers and wrenches can be building or developing objects to run in these platforms. Like, how did that come about? I think that would be really interesting for folks to know.
Yeah, so for the first of that, the thing we were trying to solve, right, was to get these heterogeneous protocols into one platform. So it did that. The idea was that once they came into our component tree, they were normalized, and that was key. That was back then to Lawnworks or Modbus or whatever the protocol was. That from there you could use them in an application way consistently in terms of historization or alarming or graphics or whatever the application may be. So, the first version did not have an open API, but, I think what we learned was people wanted to build their own connectors into the product. They wanted to do their own applications. So when we started from the R2 version to the AX version, we said, let's make this all an open set of APIs and call it a framework, right?
Yep.
And that, really was also kind of new for building automation, that, your software platform would have APIs to do whatever you want. I mean, it's really not a lot of products out there that give you an open API to do everything.
No.
Create your own components or your own connectors or whatever it may be.
Yeah. So that kind of really makes sense. And if I even look about we can cover Sedona quickly. I think that was sort of this idea of building a version of Niagara and Fox that would fit on much more constrained devices, right? But you chose to fully open source that,
Yes.
And I know ultimately it may not have ended up that way, but initially, and that was the point of it. Where did the design, or where did the idea, or where did the need for Sedona?
So, when you look at building automation system architectures today, and even still how it is back then and today, you typically have what I would call unitary controllers at the edge, your VAV controllers, your plant controllers, your fan coil units. And these are smaller power devices, tend not to run something like Java. And then you have these supervisory controllers that were running Niagara. What we saw is every major OEM, right, had their own line of unitary controllers with its own programming tools, its own software. And we said, they're all trying to integrate it into Haack. Yeah. All of the customers want one tool set. They don't want one tool for this controllers and another tool set for their supervisory controllers. So we said, let's just do a version that could run in the unitary controllers. We'll give it away, so hopefully they'll use it. And we'll integrate it into the tool set so that a systems integrator has one tool to work with their spectrum of hardware. Of course, that was, basically happened the last few years I was at Tritium. And, I would say probably the most successful company was EZIO.
Yeah.
Had a very successful line with that technology. And then it was bought a couple of years ago by JCI.
Yeah, that's right. We had our sort of prep call for this, and I didn't realize that they had been bought by JCI. Pretty interesting. And yeah, I remember when those controllers first came out, and it was for $300, you get 8 ins and 8 outs and a little mini version of Niagara running on it. And I had dreams of running my entire, home automation and all kinds of different stuff on those little controllers. It was it made it very approachable in a way that, again, I think a lot of the IoT vendors that sort of, you're doing this in 2002, 3, 4, 5 kind of era. And I think even, if you look at the stuff that came out from the true quote unquote IoT platforms of 2014, 15, 16, 17, they weren't even that far along. There was that little Wonder Bar chocolate brick, and then there was a whole bunch of stuff that was sort of along those lines, for Raspberry Pi and even Arduino now. But I use those things and they're great and you can do a lot with them. But in a way, I feel if 80% of the people who used an Arduino or a Raspberry Pi for a project had access to an EZIO or the Sedona framework early on, I think there could have been a little, there would be a different trajectory there, and there would be different adoption because, it's all there. I think that's what people realize when they start to see it or use it, is that oh, okay, wow. Yeah, no, this is light years ahead of the tools that all of us just had access to in the late, 2015, even still today. It's crazy.
Yeah.
And then, so you leave there and you go on and you start this company, Foundry, right? Which it took me a long time to understand why, right? Because I was oh my God, this, there was a little bit of I was really impressed with what you guys had done at Tritium and all of that. And then it suddenly made sense, because this was the cap on the fact that you had been building this foundation of all of this automation in the service of data collection and modeling and analytics. And so you knew now that there was this huge install base of easily queried, traversable, combinable, all sorts of cool things you could do with the data. Like you said, totally normalized.
Right.
automation and control systems out there. And so then you wrote this like completely groundbreaking new platform framework called SkySpark, which kind of allowed, again, people to do very early on some very advanced things that people still struggle to do today with, machine learning and artificial intelligence, all of that in terms of like, yeah, fault detection, diagnostics, forensics, predicting, capacity planning, all of that. So like, tell me a little bit about what made you start Sky Foundry, and where did the SkySpark idea come from? And like, what did that bring to that existing sort of like all of your prior work that you had done with Sedona and Niagara?
Yeah, I mean, it was, so Honeywell had acquired Tritium in 2005. So, it was sort of, the writing was on the wall that I was going to leave and do something new at that point. But 2009, basically, we started Sky Foundry. And the idea was, that we saw that the next chapter was connecting to devices and aggregating data at that layer, sort of a solved problem. Niagara solved it. And there was other technologies out there. Then we saw the sort of the new frontier was using all of this data, right, for the next generation level of applications, right, optimizing control sequences, analyzing for fault detection, visualizing all of this information in new ways. So that's where we got into it. I mean, I would say originally the product was very focused on, was called fault detection back then. Now it's analytics, or sort of the broader term. But that, just looking at the data, you could tell, when things weren't operating correctly. And the rule of thumb is, well, no one's ever applied SkySpark and not found that their building wasn't operating very well. I mean, it's just the buildings don't operate well. They're very difficult to make operate well. You go in and you might commission them, and a year later it's all back to the way it was. So we still think it's a huge opportunity. Especially we start talking about climate change and everything. Buildings consume a massive amount of our energy. And a lot of that is wasted just because we do such a poor job of operating them efficiently. So yeah. I still see it as a huge opportunity for, us.
Yeah.
As well as, society in general.
Yeah. And I mean, it's crazy to think that like here we are, we're in 2024 and you're still in like business. Like this is still, I mean, you guys are everywhere in the smart building space. I mean, so what is it about is it the user interface? Is it the approachability? Is it some critical network of systems integrators? Like what has made, I mean, how many people out there like have tried multiple times to start a company that lasts even for like 2 or 3 years, but like you've done this a number of times in a row, and this last one in Sky Foundry, it seems to be like it's sort of like the longest lasting legacy, and I still think, again, quite underappreciated. Like the stuff that we could do in 2008 with Sky Foundry, like I would still struggle to do in 95% of the IoT platforms that somebody would buy for the sake of IoT, right? Even when they're using it for predictive maintenance or something like that. So like, what's the secret there? I think your idea of a data model and stuff like that was something that really, like in the Sky Foundry, SkySpark, like how did the Niagara tree become that sort of idea of like the processes, the devices, the data points? I think one of the really neat things you did there was, people were really looking, like they would come in every morning and they would start at the top of their tree and they would look at alarms, and alarms would tell them some stuff, but then they would just literally go through graphic after graphic after graphic and look at every VAV to see, like, was its damper position in the right place for the room temperature, right? Mm-hmm. When you got tens or hundreds of those, like, that's a full-time job for somebody. You were like, nope. Like, what we do is we baseline what normal for a VAV looks like and what the damper position should be at different temperatures. And then we're going to automatically monitor that for you. And we're going to send you alerts, not when you guessed right and the temperature is too high or too low above a certain point, but we're going to we're going to show you the anomalies. We're going to show you the places that like maybe you didn't know were an issue, but they are an issue. Like how, again, like nobody did that before you, and like really nobody's done it since. What is the, where is that going to help customers today on, in your existing,
I think you said it, like, before there was products like SkySpark, I mean, there was sort of a manual process, right? And if someone happened to look at something, they may investigate it. And of course, the machines do that very, very well. So, I think the thing with SkySpark was that the tree structure of Niagara, right? We got completely rid of it because for that problem domain, it's not what you want. And we developed a lot of new technology, and we started Project Haystack around this idea that, modeling buildings and stuff is really, really hard because it doesn't fit a clean paradigm. If you say, what does a standard air handler look like? There's no such thing, right?
Exactly.
A lot of them are built up. They're custom. You get into central plants, they're all very custom. When you say, well, what are all the different types of sensors I may have in a building? I mean, there's thousands, tens of thousands, right? So it doesn't lend itself to modeling with traditional techniques. Like, you can't just stuff the model of a building into a relational database cleanly.
No, exactly.
So that's really the problem we are focused on is, okay, we have the operational data, right? Something like Niagara gives us the current values and historized data, but now we need to put it all together in a way that makes sense. We need to know this sensor is in this room, or this sensor is in this duct, or this is the sensor in a pipe, and that this pipe is feeding this unit, right? So that's where we got into, if we can model all of that, then we can automate the, all of the analysis of that operational data, right? And say, these are my hot water VAVs, and this is how I expect them to operate. Just look in the data and tell me when they're not operating, right?
Yep.
I'm not going to have Boiler Bob, paging through graphics anymore.
No, that's awesome. But and so and the way you did it, and let's talk a little bit about Haystack, is that you designed a way to take sort of any way that any organization or systems integrator or whatever had built their model of their building or their operation in something like Niagara, and then could map that to like a standard object model for, like you said, an air handler or a cooling tower, or, on like a manufacturing line or even a robot arm, like those types of things. And because there was pre-definition in the model of the object for what the processes would look like, what the data points would look like, then just by being able to map, like, okay, I know that, the valve position on this particular chiller in this building is this data point, you map that to the valve position, which is a well-known, well-defined, strongly typed schema in Haystack. You could just basically map everything up, and then it was like that, even one more layer of normalization on top that really allowed you to do some, like you said, like detect, really in a very unsupervised way, detect, some pretty significant anomalies and stuff like that. And again, this is something that just in the last 5 to 10 years, like serious data scientists have gotten into, like, do we use loosely typed, semantic models, or do we use strongly typed semantic models? And how much data preparation and normalization do we need to do to get this to the point where the algorithms themselves can effectively sort of parse, model, and predict, right? But you did that, and it works, right? So, can you talk a little bit about some of the use cases that you're seeing in terms of, like, you said, like fault detection, optimizing, predicting, those types of use cases, and how you've done it, I guess, because I don't remember there being a lot of actual machine learning in the platform. There wasn't really this traditional, you got to hook it up to Pandas or whatever, it was like there's something you were doing just much more like with statistics that worked really well.
We do use Pandas and that Python stack too, but I think there's a lot of simpler stuff you can do without getting into that.
Yep.
Just because most faults are very simple patterns. You don't need machine learning or regression analysis or large language models to figure them out. I say that the classic use case I take is I got a portfolio of buildings. Go look at all of my rooftop units and tell me when I'm in heating mode and cooling mode at the same time. Portfolios where it happens to the tune of tens of $1 million per month in energy costs, right? So it happens all the time. So if you want to do that, right, just for a very simple thing, the first thing you say is, how do I find all my rooftop units in my data set, right? I have that semantic understanding of that. And then for each rooftop unit, I have to find out, is it in heating mode and is it in cooling mode? And those could be valves if they're hot water and chilled water. They could be electric points if they're, direct companionshation. So, there's all sorts of different ways to look at that. But when you start talking through that problem through, right, it really makes it why you need a semantic model so bad, right?
Yep.
Because you're not going to manually do that. I'm not going to say, okay, let's look at rooftop, 5 on this building and then do the next one, right? You need to basically say, find me all my rooftops, find my heating point, find my cooling point for all of them, and then apply this analytic. And that's an easy one where you really don't need machine learning or regression analysis. It's really just looking at, intersections of period where something happens. And there's a lot of faults you can detect using something that simple. Now, once you get beyond fault detection, you start talking about optimization, then machine learning and regression analysis can do quite a bit for you.
Nice.
But
yeah, and it sounds like, I kind of felt that it's something that wasn't there with the last time that I used SkySpark, but you did eventually pull in some of the, the more traditional regression and machine learning type stuff?
Yeah, I would say we started off with some of the Java libraries. As the product is based on Java, but there's the machine learning community. They like Python, so we just accepted it and integrated Python as the Python stack into our product as a Docker container. So.
Oh wow, that's awesome. Okay, cool. So now, I feel like that's a pretty good. It's I think it's all great information and history and everything like that. I think it will really explain a lot, sort of, as like what I'm going to ask you now is more about how this 25 years of, or probably 1999 to like 26 years of experience has applied to the very specific domain of smart buildings. Like you said, like aside from some customers being cool and innovative and going outside, you've been there. But one of the things that I think, and the reason I felt so strongly about getting you on this podcast, is I think like the way you look at data and analytics and modeling, from that smart buildings is needed very much in the rest of the world, whether it's like remote asset monitoring or wind farms or whatever. And I think it's very interesting that the whole time you were doing this, if you look at the dates, they almost line up quite perfectly with, Andy and Arlen and them going ahead and creating MQTT. Mm-hmm. And so, I know you were aware of that, but it would be I would love to get your memory of that and how it went and where you saw, oh, maybe MQTT is something that we should look at, or maybe not, or maybe it's something we integrate with. And then, maybe even after that, we can talk about today, what does SkySpark look like on top of MQTT, right? Or how could SkySpark, you guys have your haystack model, but how could SkySpark use something like the spark plug specification, which, I don't know if it's coincidentally named or not, but
yeah.
It kind of has a similar feel to me in terms of a strongly typed semantic model for asset data. And then there's another thing that we should talk about here a little bit, because I know everybody would want to get your take on this. Is there's this new concept coming up in especially manufacturing of a unified namespace, which is an addressable sort of API where a business, enterprise, whatever, can access in real time all of the information from all of the physical assets, right? So, is this something that Niagara probably hinted at very early on? It's something you were doing, but now it's they just want to be able to go and get information about, the buildings, the, cars that their people are driving, or the trucks or the robots or whatever. And I think UNS is really interesting in that, because of the fact that it's largely being built around MQTT, and its ability to organize data in tree structures, but very unsort of structured in terms of its messages. It's very, very flexible. Like in this situation, the way it's rolling out right now, every UNS will be totally different. Like every company's UNS will be structured differently. And like, again, you've been looking at this problem for 25 plus years. My guess is that you think, or you would think that could eventually be a challenge. And perhaps like your experience, with Niagara and Sedona and SkySpark and Haystack and all of that might be a good sort of lessons learned for the people who are really redoing a lot of what you did there through that experience. And like, what advice would you give them in terms of, I don't know, like what not to do? Like what is already out there? What could you know what I mean? Because I feel like this is like, it's a missed opportunity for people to not understand that like there's a body of work here that's substantial and valuable, and it's worked really well. And if the theory could apply to MQTT or to whatever comes next in terms of protocols or even information, organizational theory, like, I don't know. You get what I'm saying now. Like you've got wisdom to share here with people who are essentially trying to do again what you've already done. Like how would you apply it to this new world around IoT Industrial 4.0?
Yeah. So, MQTT is a great technology. We've got it in SkySpark. We have customers who use Sparkplug too. Actually, we don't have that in the product, but it's used. But to me, when you look at the sort of the layers, MQTT by itself is a transport layer. Yep. Very good for pushing data packets, organizes things into a nice topology, but it's kind of silent on the data encoding and the semantic model.
Yeah.
Right?
Yeah.
So it's two-edged sword, kind of like HTTP.
A picture or a JSON document. We'll never know until we see it.
The transport that's used is not super interesting to me. And even the, what I call the data encoding, like, whether it's ASN1 or JSON, also not super interesting because you can write parsers for those really, pretty easily. It's the semantic model, right, is the challenge. Communicating the shared semantic model is by far way harder than the transport or deciding whether you're going to parse JSON or protobufs or ASN1, right? Yeah. So to me, that's where things happen. It's the problem. It's the space I've been working on for the last 15 years because the semantic model is really difficult, right? I say you can get a piece of telemetry data, right? Over MQTT or HTTP or, whatever it may be, and you can package it up as JSON. But how do you know what it means, right? How do you know its position in the system? What controller was acquiring it, what its unit of measure was, So to me, that's the challenge. I mean, that's what we've been working on in Project Haystack, how that works and how it all glues, because whether it's industrial systems or whether it's building automation systems or IoT systems, right? Life starts with these sensors that are connected to some local microcontroller, right? And when we start talking about what is the context of the data, typically the controller doesn't know, right? No. I mean, you may put in a controller, right? But he doesn't know that he's in room 506 and he's fed by this hot water plant and this chilled water plant and he's getting his air from this air handler, right? That you need all of that contextual information, understanding those relationships to really use the data. So once again, that's all at the semantic model layer.
Yep.
And not a lot of people, I think, are working on that. I think there's a lot of people still, fighting about what transport to use or what data encoding to use. And, to me,
it doesn't matter.
It doesn't really solve the core problem, which is we got to have a rich semantic model in order to use this operational data.
Yes. Brilliant. And I think the message that is not being received by a lot of vendors and end users even in that, the MQTT space is exactly that. Like, but it's because of a dearth of prior experience. Like, it's like, oh, like we suddenly have this ability to organize all of our real-time data using this MQTT tree structure, which
Right.
it's literally revolutionary and groundbreaking. And the fact that like they think like, oh, like I can have a second place or second broker subscribe to data points and then republish them in a different shape or a different model or whatever. And then so we can have like one MQTT API or subscriptions available for one business use case, another for another business use case or whatever. But again, the definition of how that organization is going to happen and what the format of the data looks like and all of that is like just completely wide open right now. Even if you look at Sparkplug is really more a structure around, like you said, like the metadata or like the contextual data. But it doesn't really define how many decimal points or, you know, what your, and you called them facets, which I always loved, but like what the, you know, is it Fahrenheit or Celsius? Like, how do you know? And then like, if you don't know that, how do you automatically, you know, convert it if you need to do something like present for somebody in another country or compare it to a, you know, an already centigrade or Celsius data point. So like you guys built Haystack for that, which has this body of assets and devices and all of that. But they're very, very specifically for smart buildings, right? Like I don't, you know, what is, or how do we on this other side of the IoT world, the not smart building, how do we get together and start to build a similar idea or organization around the multitude of other devices that are out there on the manufacturing side of the world, in the agriculture side of the world, in the energy, utilities, oil and gas side of the world? You know, one of the nice things, of course, about smart buildings is it's a small world. Like, you know, and how, if somebody gave you a grant to go and do exactly what you did for smart buildings in the rest of the world, or the rest of the industrial, the, you know, automation, control, and analytics world, how would you start? What would you do? Like, and then what should we do sort of to close out, you know, to help continue that vision for you just in this other, you know, domain?
Well, you know, I think the foundational ideas of Project Haystack, you know, are applicable to anything that's IoT data, right? Because temperature sensors, electric sensors, set points, all of these things apply to all domains. You know, always standard organizations in different verticals is tricky, but, you know, certainly the ideas in Project Haystack that a lot of smart people have been working on for 15 years are really viable across all of the verticals. Let's take, you know, power, for example. You know, we've spent the last few years really trying to model what are all the different ways to really model three-phase power, right? Am I importing to the grid? Am I exporting to the grid? Is it active power, apparent power, reactive power? Is it line one versus line two versus, you know, there's thousands of different ways that you get information out of, let's say, an electric meter, right?
Yeah.
And if you go to the spec sheet of an electric meter, you're going to get a human description, right? But you're not going to get a precise semantic model that, you know, this is the import active power between line 1 and 2, right?
Yep. Okay.
You know, Project Haystack solves that. And whether you use Project Haystack directly or not, any industry that's working with electricity, which is probably every industry, right, has to deal with that.
Yep.
Right. Eventually, you know, if you're still fighting over what transport to use or what data encoding to use, right, you know, JSON or protobuf or whatever, then you may not be there, but eventually you're going to get there, right? You're going to have to precisely model what all of that telemetry data means. And then, you know, the relationships between them, like, you know, when you look at, you know, for example, electric meters, you know, what are the loads it's feeding? It's feeding electric truck vehicles and, you know, fans and dampers, and they're all part of one system that has to be controlled and analyzed together to make sense of our buildings and to make them operate better.
Yeah. But who in your, you know, vision of that actually defines the models, right? Like, again, you know, I remember the very early days of Haystack. He had like it was almost like a consortium. It was a group of people who were making these definitions.
Yeah.
You know, is that the right way forward? Did you discover that that wasn't the right way forward, and maybe this is something that should be on the vendors, or like how would you do it?
It's a really tough problem because to do it effectively requires two sets of skills. One is you have deep domain knowledge, right? And two, you have some computer science data modeling skills, right?
Yeah.
Those two things are rare to come together, but those experts are out there. And when you look at what we have in Project Haystack, it's because there was a group of people who had those skills together. Like, we have very strong HVAC knowledge and electrical knowledge today. But maybe not some sort of industrial like process control, right?
Yeah.
But it's all the same, in terms of how you go about defining these semantic models. One of the things that we got Project Haystack got is a U.S. Department of Energy grant to develop a new technology we called Zeto. And the idea of Zeto is, at least for the unitary controllers we have out there, VAVs, electric meters, flow meters, these pieces of equipment that have the same function, right? Let's create a template and really model everything semantically. The thing that's killed me even today after the decades I've been in this industry, like if you go and buy an electric meter with Modbus registers, you're going to get the register map as a PDF file, and you're probably going to type the registers in, and you say, oh, I got to do this conversion and this to actually get the value.
Mm-hmm.
I mean, that should all be in a standard, machine readable format. And if we can actually put the semantics in there, with a standardized understanding of exactly what each of those registers means, think how much time we could save. I could pull that in directly into an analytics or a control platform without this manual mapping that people are doing over and over again.
Yeah, that's true. That's kind of crazy. And I wonder, like, are there any devices out there along those lines that actually just brought, if you think back to like the BBMD and the BACnet broadcast idea, like the point discovery there was let's say it was basic, but I think it was pretty good. And the same thing with Niagara. Like, is that the answer? Like, should any device that supports MQTT natively, should there be a topic that sort of just automatically broadcasts like the data model and all of that metadata, or is it something again that you think should be like physically handled or layered in at a like human managed semantic layer?
I mean, I think it depends on the device and the application. So, certainly what I would call fixed function devices, unitary controllers, right? We know ahead of time what they're going to mean. No one should have to, manually enter that ever again, whether the device broadcasts it or includes it or points you to a location on the cloud. That's the layer one. And that layer's, that is not solved today. We're hoping to solve that with our technology Zeto. When you get into, PLCs and programmable controllers, the semantics are defined in the field. You don't necessarily know till some systems integrator wires it up to the, the pump.
Starts pulling.
So we still need tools that are modeling this in the field. And then, as we move up a layer, the contextual information. A fixed function device doesn't necessarily know contextually what room he's in, where he's located, where he's getting his power from, et cetera, till someone tells him.
Yeah, that's true. The interactions, because that's all like totally ad hoc based again on like how it was installed and stuff like that. So I think we could do better. Like, I still think that like there's going to be a connection made, I hope, in somebody who's going to take a look and go back and maybe look at Haystack and think about, is this something that could apply to like a UNS construct, or, maybe Sparkplug is closer and headed in the right direction, but maybe there are these sort of adaptions or whatever that we could bring into it so that, we expose the full capabilities of that, like being able to actually use the information later, right? Without having to, it's like, we used to talk about this at Turner, was like, it took a year to install the controllers and 2 years to figure out how to like analyze them and get all the data and stuff like that, and it's just like, it's just a series of projects. I do want to close with one sort of like interesting, maybe thought-provoking question. You're obviously, futurist, technologist and stuff like that. What do you think the potential for using large language models and other AI to actually define the semantics could be? Like, say, for example, if you could just feed it the train, air handler manual and stuff like that, and it could learn best practices and stuff like that, what would be the possibilities of using like something like ChatGPT to say, hey, I need a standard list of data points for this entire bill of materials for this job and stuff like that. Yeah. Do you think that's something that's are we?
Yeah, I think it's going to be a really important technology. So, when you look at data-driven applications, better control, better analytics, whatever it may be, right? The major barrier today is still the cost involved in modeling the data. It's typically done with some machine learning and some tools today, but it's still, there's a human in the loop. Large language models have the ability to really take some of the cost out of that, at least in understanding the way the system is architected.
Yep.
Some of the things that we've seen very promising is if you take your old style spinning fan graphics right out of your system and run those through an LLM, right, you can make a lot of inferences about what all of your data means, right? Oh, that point was driving the fan of the graphic, and this point was driving the damper, right? So I probably know now what those points are, even if they may have been named, AI1 and AI2 or whatever they, right?
That never happened.
If they even had a valid name.
Yeah.
Because really we're driving that model mostly from the names that the contractor left in the system, which could be consistent and could be not. But so I think there's a lot of opportunity with the LLM to automate more and take cost out of that process. So I think it's going to be a really important technology.
Yeah, that's awesome. Well, cool. I hope we can work on that together at some point, because for me, I think, LLMs, it's sort of in its like circus sideshow period right now. And I think because of that, like people have a lot of really strong opinions of it one way or the other. I think like anything, the real value is somewhere there in the middle. And I think about like in allowing it to take like lots and lots of historian data and come up with some theories that could be tested against real-time data and do all of that. Like it could really augment and like you said, speed up and improve like a lot of the stuff that, you've been driving now for longer than just about anybody, I would say, honestly. And I know it would be really cool to learn, I think, at some point from you about how we could easily integrate, a SkySpark server with, an HiveMQ, broker, just to even do a demo or to kind of show people like what this framework of modeling and UNS and analytics or we call it UNS, but you call it semantic modeling, could look like, through the lens of an application that's, time tested and time proven. It would all apply when I feel like I'm like, it does not care if it's a wind turbine or an air handler.
Yeah, for sure.
Cool.
Yeah, I think there's some exciting opportunities there. So I thought we covered a lot of ground.
Yeah, we did. It was good. It was good. And I think like, the message I really want to get across to people is that like there's no need to reinvent the wheel on a lot of this, right?
Yeah, like I said, there's a huge opportunity. Like if we can start getting to the semantic model layer, like there's so much opportunity to make things operate better.